Hi guys, and welcome to this next lecture. This time we're dealing with parallel circuits with 3 resistors, which is just a little expanded compared to our previous lecture with 2 resistors. Now we're going to look at the total resistance of the circuit. We'll have a look at how the current actually splits up through the different individual resistor branches, and we'll talk about the voltage drops across each resistor as well. We'll have a look at a circuit simulator, and then if we have time we'll do another circuit like this and do some more calculations. In an up-and-coming lecture, perhaps the next lecture, we'll actually have a look at practical examples or practical uses of connecting things in parallel like this. So let's get started with this one. Now, before I actually do some calculations, recall that in a parallel circuit, the voltage across each component is the same. Why are they the same? Well, if we if we connect up R1 to the power supply, we see that it's directly connected there, as in the top leg is connected straight to positive while the bottom is connected straight to negative. It has a direct connection with no components in between, therefore we get 6 volts. If we have a look at R2, it is the same thing. We have a short circuit piece of wire going straight from the top of R2 to positive, and a short circuit piece of wire going straight from the bottom to the negative. Not bosom, bottom. Therefore it has 6 volts. R3, same thing. Positive of the power supply, straight to the top of R3, negative of the power supply, straight to the bottom of R3. It has a direct connection to the power supply. It also has 6 volts. So in a parallel circuit, every resistor will have 6 volts in this example. But what happens to current? Well, if we follow through the electrons going this way, we get to a node. In fact, there's 4 nodes in this circuit, 1, 2, 3, and 4. At this node, it's going to split up. Some of the electrons are going to go that way, and some will go this way. So the current actually divides. That's why we call it a current divider. We then get to this node, and it will divide again, like this. We come up to this node, and this current are going to join together, so they recombine to give us the current going through here. In fact, the current up the top here is the same as the current there. Down here, it just hadn't split up yet. Up here, it had joined back together from previously being split. We then get to this node, and this current add back together, and we're back to the same amount of current that we had down here. So that there is the same as that. So we're going to go through some calculations. We'll look up the circuit simulator, we'll compare the two, and hopefully you'll start to get a bit of a aha type thing going, oh, I see what's going on now. That would be the goal. I guess I wouldn't be doing these lectures if I didn't think that we could get somewhere with them. Otherwise, I really shouldn't be doing this. So the first thing to find is RT. What I mean by that is if we had one single resistor over here connected to a 6-volt power supply, same as this one, what value would that be to give us exactly the same amount of current as these 3 in parallel? So in order to figure that out, we could use the product over sum method. In fact, I spoke about this when we were doing the 2 resistor parallel circuits. Product over sum is really good because, for example, if we just had these 2, we'd go 1K times 2K over 1K plus 2K. And that would give us the equivalent or the total resistance for just those 2. However, the problem with the product over sum is you can only do it with 2 resistors at a time. And if you have a look, we've actually got 3 in this case. So we could use a product over sum. We'd have to do it multiple times in order to get something that looks like this. So I'm going to go with the reciprocal method, which allows us to put all of these circuit calculations for R1, R2, R3 all in one smooth formula. And then once we've done that, we'll get the answer that we're looking for down here. So 1 on R1 plus 1 on R2 plus 1 on R3, and if we had a 4th resistor we'd also put down the bottom there 1 over R4 and so forth. So let's put some figures in. 1 on 1K plus 1 on 2K plus 1 on 4K. And we'll talk about these resistor values in a moment. Let's bring up the calculator. So I'm going to do the stuff down the bottom, just like in the previous lecture. We do the stuff down the bottom first. Then once we've got all of that, we then do 1 divided by that. So 1 divided by 1K plus, now we've got to plus this one, and we have to put that in brackets. Open bracket, 1 divided by 2K, close the bracket, plus, open the bracket for the last one, 1 divided by 4k. Close the bracket equals, now that answer there is this answer for all that stuff underneath that line. So in order to get the answer, we now need to do 1 divided by what we just found. So on your calculator, you should have like a second function or a shift function. So do 1 divided by the last answer. Equals, and we're getting 571.4, and we'd round that up to a 3. 571.43 ohms. So this resistor here, if we were to make that a 571.43 ohm resistor, the amount of current we would get going there would be exactly the same as these three in parallel. Exactly the same. Now let's discuss these three in parallel just a little bit more. We're going to have a certain amount of current going that way, certain amount of current going that way, and finally, what do we like here? Let's go light blue, a certain amount of current going that way. We're going to start off with the total current this way. That total current would split up, some that way, some that way, some that way. And then up the top they recombine. That plus this, and then that plus this, we're back to the total again. But how much current do we have in total? Let's go red. Well, to do that we need IT. Oops. Let's go back to a proper pen. Now that we've got the total resistance, we can work out total current. We need the total voltage, which is 6 volts, divided by total resistance, which is 571.43 ohms. And the total current we'll get is going to be 6 volts divided by 571.43 ohms. And I'm getting 10.4 with lots of 9s, and that's milli, because it's negative 3. So we'll round that up to 10.5. 10.5 milliamps. So the amount of current here is 10.5 milliamps. Same here, 10.5 milliamps. But there's more calculations we can do. We can figure out how much of that 10.5 goes up each one of these resistors. We'll start with the green one. So we've got a 1K resistor here connected straight to 6 volts. So to work out the current through that resistor, we just need to do 6 volts, which is the voltage across it, divided by the value of it, which is 1K. Do that on the calculator. 6 volts divided by 1K is 6 milliamps. So notice we're starting with 10.5 total. That's all we've got. That first resistor actually gets 6 milliamps of that. It gets more than half. That's because that value of resistor is the lowest resistor. 1K is the smallest, 2K is twice as big, 4K is 4 times as big. The bigger the resistor, the less current. So that's why we can see the 1K is getting the vast majority of our total 10.5. What about R2? Well, has the same voltage because it's connected straight to the power supply, 6 volts. It's now twice the resistance though. So hopefully in your head you can think, well, if it's twice the resistance and it has the same voltage, there must be half the amount of current going through it. Now if you thought that, you'd be correct. 6 volts divided by 2K, we're now only getting 3 milliamps going up that way. Half of the 6 that we get there. So we start with 10.5. 6 goes that way. We would be left with 4.5 this way. Of that 4.5 going up here, 3 goes up there. So how much should we be left with this way? Well, we should be left with 1.5. Start with 10, we lose 6, we should be left with 4.5. We lose 3, we should be left with 1.5. Let's do that last one. The current through resistor 3 is going to be 6 volts because it's connected straight to the power supply, divided by 4K. Just going to turn my sound off there. So let's do that. 6 volts divided by 4K, 1.5 milliamps. And just so we can get rid of some confusion, I'm going to get rid of that little guy there. 1.5 milliamps. So 1.5 plus 3, there's our 4.5, plus 6, we're back to our 10.5. It just simply splits up. Now notice the smallest resistor got the most current, which makes perfect sense, because the lower the value of resistance, the more current you do get. We can also see with the particular values of resistors that I've chosen, we start with 1K and then we double that to 2K. As we double the resistance, we halve the amount of current. As we double from 2K to 4K, we halve the current again. 3 milliamps has gone to 1.5. We can work with these ratios. The bigger the resistor is, the less current you get going through it. The other way of saying that is the smaller the resistor is, the more current you actually get going. So even before we do any of these calculations, we can have a look at it and go, well, they're all in parallel, which means they're all going to have the same voltage. This one's a 1K, this one's a 2K, this one's a 4K, but without doing any calculations, I can see the 1K should have the most amount of current, the 2K would have the next most amount, and then the 4K would have the least. And that'll be really handy when we talk about troubleshooting later on. Okay, finished with the calculator for now. Let's have a look at the circuit simulator. We've got a 6-volt power supply, a 1K resistor in parallel with a 2K, in parallel with a 4K. How much total current? 10.5 milliamps. Is that correct? Yes, yes it is. That's what we calculated. Now how much did we say goes through this one? 6 milliamps. Yes, that's exactly what we calculated. How much are we left with then? If we start with 10.5 and we lose 6, there's our 4.5, which is exactly what I was saying. Of that 4.5, how much goes up this way? 3 milliamps. Exactly right. That's what we calculated. If we started with 4.5 and we lost 3, how much should be here? Well, we've got 1.5. Again, mathematics is lining up. Good job, mathematics. That 1.5 comes up through the 4K, and we get to this node up the top, and it recombines with the 3 to give us 4.5, same as what we had before it split. 4.5 recombines with 6, so we get 10.5 again, same as what we had before it split. So that's what's going on with our parallel circuits. Now the electron's flowing, splits up again because there's 3 resistors, and then it just recombines. The lower the value the resistor is, the more current you get going through it.